The creation of this video lecture was made possible through the use of the following open source tools. This video discusses the use of libraries of functions along with one-dimensional fixed-length arrays. Discuss the use of type definitions along with one-dimensional arrays. We will define a value returning function for generating random numbers within a specified range, along with functions for initializing one-dimensional arrays, all within a library and a namespace. Finally, we will make use of the getLine function for input. Let us briefly consider one-dimensional fixed-length arrays. One-dimensional arrays are linear sequences of values of the same type. Each of these values can be accessed by way of an integer index. To create an array, its type, name, and length must be specified. This length must be known at compile time, so is typically either a named constant or literal value. Their lengths cannot be changed. The type signature of fixed-length arrays can be quite long and cumbersome to work with. Therefore, it is common to make use of type definitions in order to create a short type alias for ease of use. In general, array operations are performed on an element-by-element basis. As with strings, these elements are accessed via the indexing operator. C++ does not provide for range checking of array indices. In order to perform operations on an entire array, it is typically necessary to make use of functions. Arrays may be initialized through the use of initializer lists. If the size of the array is not specified, the length of the initializer list is used. If the size of the array is known, and a shorter initializer list is provided, then the remaining elements are zeroed. Use of initializer lists in this way is only possible on array creation. Arrays may be passed to functions as parameters. The memory address of the first element in the array is what is passed when an array is passed by value. This has the effect of making it seem like the array is passed by reference, since the elements in the array may be changed. The memory address of the first element in the array is what is passed when an array is passed by value. This has the effect of making it seem like the array is passed by reference, since the elements in the array may be changed. A constant integer length is defined, along with a type alias through the use of a type definition. The array is created and its contents are initialized to 0. We will now create a function for printing the contents of the array to the standard output stream. The for loop will generate array index values from 0 up to the length of the array minus 1. The indexing operator allows each element in the array to be retrieved and sent to the output stream. The function is called with the array passed as an argument to that function. The contents of the array are printed to the terminal window. As mentioned, the initializer lists can only be used when the array is first created, so in order to be able to initialize arrays that already exist, we will need to create a function to do so. The initialization parameter is stored in the array at the position specified by the index. The function is called, and both the array and initialization parameter are passed as arguments. We will now discuss the generation of pseudorandom numbers within a specified range through the use of a value returning function. The ranged random function will return an integer and will take as input two integer parameters. These represent the minimum and maximum value of the specified range. Both the C standard library and C-time library are necessary for this approach to random number generation to work. In order to generate a sequence of pseudorandom numbers that appears to change all the time, the random number generator's seed value needs to be set to a value that changes all the time, such as the time. For a full discussion of the logic behind this algorithm, please see the BPL exercise regarding the generation of pseudorandom numbers. Building on our previous work, we can now create an initialization function for arrays that will initialize arrays to random values within a specified range. For the purpose of this video, we will generate values in the range 1 to 100 inclusive. Numerical arrays are often not directly output in their raw form, but are often converted into something more easy to interpret, such as a sequence of characters. A for loop once again generates all of the valid indices from 0 up to the length of the array -1. The value is then retrieved from the array and inspected. It is then tested to see which range it falls into, and a different character representing an imaginary letter grade system is output instead of the raw numerical value stored within the array. We will now place the functions that we have created into a programmer-defined library and also into a namespace. Libraries in C++ are typically split into two separate files, the interface file and the implementation file. The header file forms the interface, and contains the prototypes to the functions which are being externally exposed from the library. These prototypes consist of the return type, name, and parameter types for the functions in question. Additionally, any constants or type definitions that may be useful for programmers using the library are also included in the header file. The implementation file, which has a CPP extension, contains the implementation details for all of those functions. The advantage of this system is that when any changes are made to a library, only that library's CPP file needs to be recompiled. The rest of a large project does not need to be. This can save considerable amounts of time. As you can see, both files and a library have the same name. They differ only in their extensions. Additionally, the interface file is linked to the implementation file by having the implementation file #include the header file using double quotes instead of single quotes to indicate that this is a programmer-defined library rather than a system library. Namespaces are used to group related identifiers together so that they don't clash in larger projects. They need to be defined in both the header file and the CPP file for a library. In addition, they also need to be used in the main CPP file. It's important to note that includes are local to the current compilation unit, basically the CPP file that you're currently working in, and as such, you may need to have several copies of the #includes across different CPP files in a larger project. This is the reason for the guard conditions in the header file, to prevent multiple inclusions in large projects. We will take a look at the getLine function, which will allow us to read in an entire line of text at a time, rather than a single word, i.e. a whitespace delimited sequence of text that we were previously able to do using the stream extraction operator and the standard input stream. It is important to note that trying to create a new variable within a case statement will cause an error with the C++ compiler. For this reason, you may sometimes wish to introduce a new block within the case so that these variables may be safely created. Alternatively, you can move all variable creation to before the switch statement. Programs that make use of both getLine and cin with the stream extraction operator can encounter problems that result from the new line character being left on the input stream by the stream extraction operator, and getLine stopping when it encounters a new line character. This interaction can be avoided by using cin.ignore to remove the extra end-of-line character on the input stream. We thank you for your attention.